A very good day to Doctor and all our teammates and also our classmates. So today we'll be presenting about communication principle, group assignment 2 and mission 3. We are group 3 and we consist of Irfan, Dunhui, Darshan and me, Hui Ying. So we'll be starting the presentation.
Sampling theorem, also known as Nichols' theorem, shows that a signal can be exactly reproduced if it is sampled at a frequency greater than twice the maximum in the signal. Proper sampling occurs when an analog signal can be exactly reconstructed using the samples. There are three types of sampling method, which are ideal sampling, natural sampling, and flat top sampling. For ideal sampling, the impulse sampling is performed by multiplying input signal with impulse train of period t, and the graph usually shows like arrow shaped. For natural sampling, the impulse sampling is performed by multiplying input signal with pulse train of period t, and the graph shows like a bar with following the curve of the input signal. And lastly, we have flat top sampling, where noise can be easily removed through the flat top sampling, and flat top sampling makes use of the sample and hold the circuit. So for flat top sampling wise, it doesn't follow the curve that much, where it will still ends up with a flat surface on top.
There are several types of pulse modulation. One of the pulse modulation is pulse code modulation. It is a technique that converts analog signal to digital signal. There are three processes in pulse code modulation, which are sampling, quantization, and coding. In sampling process, it converts an analog signal to a discrete signal. In quantization process, it quantizes the sampled signal into voltage levels, each represented by binary numbers. In coding process, it converts binary numbers into a sequence binary pulse patterns. In quantization process, it can be divided into uniform and non-uniform. For uniform quantization, it is a quantization process based on the bit depth using a fixed quantization interval. Bit depth, represented by n, is the number of bits used per sample. In this case, there are 3 bits used per sample. Sampling rate, represented by Fs, is the number of times per second a continuous signal is sampled to create a discrete signal. Bit rate, represented by Fb, is the number of data transmitted per second. Bit rate is affected by bit depth and sampling rate.
So hello everyone, moving on to multiplexing, you must be wondering what exactly is multiplexing. I want you to imagine you're at the bustling train station. Multiple trains are arriving and departing, all sharing the same set of tracks. It would be chaos if all the trains tried to use the tracks simultaneously. Collisions, delays, and a complete mess happen. So this is where a system like multiplexing comes in. It acts like a smart traffic controller, ensuring that each train gets its own dedicated time slot on the tracks, preventing any collisions and keeping everything running smoothly. The purpose of a multiplexer is to allow multiple signals to share the same channel without interfering with each other. This makes communication more efficient, as you can send more information using fewer resources. Multiplexers are used in many everyday technologies like your phones, television, and internet. So now we are looking into the first type of multiplexer, which is frequency division modulation, or known as FDM. On the left, you see three separate input signals. These represent different messages or data streams that need to be transmitted. Each has a unique waveform as shown by the different shapes of signals. Each input signal is then modulated with a specific carrier frequency. Modulation essentially shifts the signal to a different frequency range. The modulated signals are then combined using a combiner or adder. This creates a composite signal containing all three original signals, but now they occupy different frequency bands within the overall channel. The combined signal is then sent through the transmission channel. This could be a cable or any other medium that can carry the signal. The separated signal are then demodulated to recover the original messages. Low pass filter to remove any remaining high frequency components. So now we are looking at time division modulation, or TDM. You can see that on the left we have four different sources, which are A, B, C, and D. This could be anything generating data or signals like computers, phones, or sensors. Multiplexer takes the input from each source and assigns it to a specific time slot within a frame. In this diagram, the frame is represented by the colored blocks. Each color corresponds to a different source. Notice how the multiplexer systematically allocates a slot to each source in a repeating pattern. The combined signal, containing data from all sources in their allocated slots, is then transmitted over the single communications channel. This channel could be a wire or a fiber optic cable. At the receiving end, the demultiplexer performs the reverse operation of the multiplexer. It separates the combined signal back into its individual components based on their designated time slots. The demultiplexer then directs each separated signal to its intended destination. So now moving on to the comparison between FDM and TDM, where FDM uses analog signal type and TDM is digital. FDM is less efficient due to cut bands, for example radio, and then TDM is more efficient, such as cellular networks and data communication. FDM don't have strict time synchronization, but it needs cut band, while TDM is strict time synchronization.
Now let's see the recent enhancement in multiplexing, which is space division multiplexing (SDM) using multi-core fiber (MCF). From the name itself, we can know that MCF consists of multiple optical cores within just a singular fiber cable, which allows vast amount of data streams simultaneously. So the researchers and companies have developed a 19 core fibers and multi-mode cores, achieving transmission of record-breaking 1 petabyte per second over long distances. Let's see the impact and benefits of the SDM MCF to the society. Firstly, it enhances global connectivity, where it increases bandwidth to meet the growing demands of 5G networks, streaming services, and cloud computing. Nextly, it's also very efficient in energy-wise, as it reduces the need for additional physical cables, which eventually lowers the energy consumption in data centers and reducing the environmental footprint. Next, it also cost effective. As I said just now, it reduces the need of additional physical cables, where more data can be gone through in a single fiber. So this decreases the cost per bit, making high-speed internet more affordable globally. And lastly, it supports the emerging technologies that we use every day now, which is like AI, IoT, and many other autonomous systems. Now let's discuss the misconception in multiplexing. The first one is TDM cannot support asynchronous communication, which is not true because it has buffers and dynamic time slot assignment to work asynchronously. Asynchronous TDM actually allows efficient use of bandwidth by allocating slots only when the data is available. The next one is TDM is only suitable for low speed communication, which is also not true because modern TDM nowadays are integral to high speed networks, including 5G and other fiber optic communications, where time slots are used to multiplex high bitrate signals. And lastly, the FDM requires excessive bandwidth and is inefficient, which is not true also because those advancements in FDM nowadays, like orthogonal frequency division multiplexing (OFDM), enables efficient bandwidth usage by overlapping subcarrier frequencies with minimal interface.
Recently, adaptive power efficient pulse position modulation for optical communication has become advancement designed to optimize data rates and power usage. These systems can dynamically adjust transmission speeds based on channel conditions, ensuring efficient performance. Additionally, they also reduce power consumption, promoting sustainable operation. Innovations in pulse position modulation have also enhanced data transmission rates and improved spectral efficiency. The impact and benefits of adaptive power efficient pulse position modulation on society are significant. Firstly, it enhances connectivity by providing high speed, reliable communication in rural and remote areas, supporting global internet access. Secondly, it is energy efficient and sustainable, reducing energy consumption in communication networks and contributing to eco friendly solutions. This technology also supports low power devices such as IoT sensors, enabling smarter and more sustainable technologies. Lastly, it also offers resilience in adverse conditions, ensuring reliable communication even in challenging environments like fog and turbulence. This is critical for emergency response and disaster management networks. There are several misconceptions about adaptive power efficient pulse position modulation across different aspects. Firstly, many believe that the exposure to laser light is harmful to humans, but actually these systems are designed with safety threshold in compliance with IEC 60825-1 standards. Secondly, it is often assumed that Wi-Fi will solve all connectivity challenges and rule the broadband wireless world. In fact, technologies like pulse position modulation in optical systems are essential for areas where Wi-Fi struggles, such as long-distance communication and interference-prone environments. Thirdly, some think that the range of free space optical communication is too limited due to atmospheric effects. In reality, it is less affected by issues like rain, electromagnetic interference, and multi-path scattering, making it highly effective in suitable conditions.
This is our reference page where we use these documents to do our assignment.